Hello there. Let's maintain an AVL tree by rotating some nodes after we add a new node that messes up the whole tree. Okay, I hope that before you watch this video, you've seen my other videos where we talk about what is a binary search tree, how to define it, terminology, how to build a tree, search through the tree, all the stuff for the tree, the binary search tree. And then my other videos where we talked about what is an AVL tree, what is a rotation, what are the different types of rotations, why would you want to rotate, how do you do the balance factors, all that stuff happens in previous videos. So search the video history. Anyway, so for now, I'm going to assume that you know all that because you watched the videos, and now we're looking at an AVL tree. Maybe first we're going to try to decide if it's a valid AVL tree, and then we will add a new node, which will probably mess the whole thing up and force us to do a rotation to get the tree back in balance. Okay, so the first thing I'm going to do is this is an example tree. It's got some nodes. And I'm going to compute the balance factors for every single node, just to double check. Remember, the rule that we're using is if an AVL tree has a balance factor of 2 or worse for any node, then it's considered invalid. The tree itself is just a binary search tree, not an AVL tree, until we fix the imbalance. So the 44 node, wait, hang on, that's actually wrong. I don't know why I even typed that number there. Oh, because I was saying 2. First thing I want to do is do the balance factors for the leaves because they're the easiest. All the leaves have a balance factor of 0 because they have no difference in left subtree versus right subtree height. The 50 node is also kind of easy because its left subtree and right subtree have the same height, so that's just a 0. 17 is a little bit more tricky. It's got one node hanging off the right side, so its right subtree height is 1, its left subtree height is 0, so absolute value of 0 minus 1 is just going to be 1. So that's not perfect, but at the same time, that's acceptable. We can just sort of move on. Remember, only 2 or worse is going to make us stop. We look at the 78 again. Let me just, or for the first time we look at the 78. Let me just do this the hard way to make sure everybody's on the same page. For the balance factor of the 78 node, we look at the height of the left subtree, which is 2, and then we look at the height of the right subtree, which is 1. And so if you take the absolute value of 2 minus 1, that's going to be 1. So actually the balance factor of the 78 node is okay. This is maybe a good time to point out the fact that we don't really care about mass or weight. We don't care that there are more nodes on the left. We just care about the height of the left subtree. So I'm going to duplicate this slide to continue. So far so good. Every node seems to be okay. We'll look at the 44 node. You can probably eyeball it because, well, I mean, for me, when I want to eyeball balance factors, I just look at the left subtree versus the right subtree. Notice how there's like one level of difference in height. We could do it the hard way if we wanted to. So like the left subtree has a height of 2, right subtree has a height of 3. So 2 minus 3, absolute value, that's going to be 1. Or just that one line that I drew before, which was the difference. So that means this whole tree is actually okay. It is a valid AVL tree. Nice. Video over. I'm just kidding. Let's add a node that will screw everything up so that we're forced to do a rotation. So I'm going to add the number 54. Let me just try to select an existing node here, duplicate it. I'll change this to a 54. Then we'll figure out where the 54 node actually belongs. Hopefully you've already become an expert at binary search trees, so I'm just going to do it real quick. We show up top here. 54 belongs on the right. We look at the 78, it belongs on the left. We look at the 50, it belongs on the right. We look at the 62, it belongs on the left. So the 54 belongs right there as the left child of the 62 node. So I'm going to go ahead and do my little connecting line indicating that the nodes are now pointing to each other. The 54 thinks its parent is 62. The 62 thinks its left child is 54. And now we have to recompute the balance factors. So obviously the node we just added, it doesn't have a balance factor, so we have to recompute it. So I'm going to put a 0 there. But we have to work our way up the tree until we hit the root node, recomputing all balance factors along the way. We don't actually, I'm going to do marks here to make sure that I don't forget. We don't actually have to recompute, the 17 or the 32 or the 88, because those nodes are not possibly going to, or actually even the 48, because those nodes are not possibly going to be affected by the 54 node, because balance factors are only affected by nodes that are underneath. So these nodes off to the side, or even nodes below, wouldn't be affected. So we're only going to compute the 62, the 50, the 78, and the 44, working our way up to the root node. As soon as we hit root, then we're done recomputing. So the balance factor for the 62, I'm going to eyeball that. That's going to be a 1 because left subtree height is 1, right subtree height is 0. So far, so good. As soon as we see a 2, we probably need to stop and rotate right away. Again, as I said in a previous video, we probably will see that the root node's balance factor is bad. But if we compute the whole tree and then just decide, I don't know, like the root node is going to be rotated, we'll probably rotate incorrectly. You want to rotate as low as possible first, because rotating lower in a tree is probably going to fix nodes that are higher. So recomputing the balance factor for the 50, that's going to be a 1 because left subtree height of 1, right subtree height of 2. Take the absolute value of the difference there. We go up to the 78 node, and this one is going to be bad because you can see that the left subtree has a height of 3 and the right subtree has a height of 1, so the balance factor is going to be a 2. It's at this point, since we just started by inserting the 54 and worked our way up, that I would stop and do a rotation. But just for the purposes of this tutorial, I'm gonna compute the root node just to show you what's going on. The height of the left subtree off the root node is 2. The height of the right subtree is 1, 2, 3, 4. So that means the balance factor of the 44 node also has a 2. So at this point, it might be a little confusing if you don't remember that you kind of have to stop as you're working your way up, or at least rotate the lowest possible node first. You might be confused. You know, which one do I rotate? Do I rotate the 78 first, or do I rotate the 44? If we were to rotate the 44 first, the root node, you know, we could do it, but at the same time, there's a chance that it won't actually fix the 78 node, and there will be other stuff underneath that is bad. And so it'll cost us more work to do it that way. So instead, we're going to stop at the 78 and do our rotation. So remember we said in a previous video that we'll choose the first node that is out of whack as the Z node. We're looking for X, Y, and Z. I'm going to write X, Y, and Z here. X, Y, and Z. Now, how do we choose Y? We go down to a child of Z, and it has to be the child that has the taller subtree. Notice how the left subtree of the Z node has a height of 3 and the right subtree has a height of 1, which means we definitely need to go left to find the Y node. So I'm going to put Y right here. If the left and the right subtree had the same height, then it doesn't really matter which one you choose. Maybe try to be consistent, but definitely we have to go left this time because that's the taller subtree. Again, look how tall it is. Okay, now we need to look for the X node. Again, we have to take the left or the right child of the Y node, or just like a grandchild of the Z node. That is definitely a child of the Y node. We have to choose the taller subtree, so we could not put X as 48. We can't do that because that's not the taller subtree. Instead, the X is going to be the 62 node because that's the taller subtree. Now we have chosen our X, Y, and Z node, which means I'm going to just type some stuff up here real fast. I'm going to do X is equal to 62, Y is equal to 50, and Z is equal to 78, just as a reminder. And this is kind of similar to what you would do in the code. I mean, on these diagrams, us humans, we have to like rearrange things and name the types of rotations and so forth. In the code, it's actually really easy in comparison, because all you have to do is produce an in-order representation of the 3 node pointers that you received, X, Y, and Z. Let's say we have a function called rotate. We don't even have to remember the types of rotations. You just grab X, Y, Z, and then you order them and call them A, B, and C. Let's do A equals something, B equals something, C equals something. So A is going to be the least value because, again, this has to be a binary search tree before it can be an AVL tree. So 50 is going to go on the left. That's the only place that it could go. And then 62 in the middle, and then 78 on the right side. And then I'm going to just, maybe I'll copy and paste this here. This little trinode subtree. Will that work? Yeah, so I don't have to draw this again. I'm going to erase some of this stuff. Ow, come on, man. I'm going to erase some of this stuff just to make it a little more neat. Then I'm going to replace the values in these nodes with just X, Y, and Z. So, sorry, A, B, C. So A is going to be 50. That's the leftmost node or the least value. And then B is going to be 62. And then C is 78. Before you continue, make sure you've actually drawn a valid binary search tree, because if you haven't, then your AVL tree is not going to end up being valid either. It always has to be a valid binary search tree, so the order has to be correct. So if you were thinking about, well, how come we can't put the 78 in the middle, or how come we can't put the 62 on the left, what would have happened? Well, it would have been invalid. Or you would have ended up with like a straight line or something that wasn't the target pattern for a rotation, which is supposed to be a perfectly balanced trinode subtree. Okay, so now we've got X, Y, and Z, and A, B, C, and we have our output pattern here, which is going to basically take away from these three nodes. The next thing we need to do is take into account any nodes that come underneath nodes from the output pattern. So our X, Y, Z, I guess you could say input pattern too. Let's look at, X, for example. So like the 62. Did it have any children that are not accounted for in the output pattern? Actually, yes, it has a 54 node. So this 54 needs to go somewhere. We can't just like erase it from the tree. So I'm going to move it down here, just so I don't forget it. Then we look at the Y node. What children did the Y node have? It had a 48 as a child and a 62 as a child. The 62 is actually already handled in the output pattern, so we don't need to worry about that. But the 48 was not handled, so we got to put that somewhere too. So I'm going to move that down here. Now we look at the Z node. The Z node had 50 as a child, as a left child. That's already handled in the output pattern, so we don't need to worry about that. It also had 88, and that is not in the output pattern, so we have to do something with 88. So I'm going to move that down here too. I should also point out, I think in a future video I'm going to do a more complicated example where some of these nodes that are children of the output pattern, they might have children of their own or descendants of their own. If they do, don't rearrange any of the descendants. So anything that was below 54, just leave it in place, hanging exactly where it was already off of the 54. Same thing for the 48. If it had any children of its own, just leave them in place. Don't touch them. Don't touch any descendants. So now that we've done this, whoops, dang it. Let me copy this in a good way instead of a bad way. Okay, let me erase this real fast. X, Y, and Z. Nope, that's going to screw me up. I'm going to forget. Okay, now we have to place these nodes of the output pattern in their appropriate position. Like, where do they actually belong? Well, remember, this is supposed to be a binary search tree, so there's actually only one place that the 54 node could ever go and still give us a valid binary search tree. So, I mean, think about it for a second. Could it go on the left of 50? No. Could it go on the right of 62? No. It has to go in between the 50 and the 62. Otherwise, we wouldn't have a valid binary search tree. So I'm just going to stick it right there, maybe a little bit lower to make this a more beautiful diagram. Then I'm going to do my connecting line real fast. So I'm going to do this. So it's the right child of the 50 now. Notice how before it was the left child of the 62. So then, again, we're just really disconnecting pointers and then rearranging them. So this 48, it can't be on the right side of 62. It has to be on the left side. It can't be on the right side of the 50. It has to be on the left side. So the 48 must be the left child of the 50. Again, you must end up with a valid binary search tree or you've done something wrong. So I'm going to just kind of do this here. And then same thing for the 88 node. There's only one place this could go. It can't go on the left of 62. It has to go on the right of the 78. It couldn't go on the left of the 78. That would be bad news. So I'm just going to place this here and then just make a little connecting line. Okay, now I'm going to double check to make sure that I didn't forget any other nodes, because when you're working with a diagram, you might forget a couple of nodes and just sort of like erase too many nodes without putting them in the output pattern. If you're rearranging pointers, it's fine. You wouldn't have to worry about any nodes that came underneath these nodes because they would just remain attached in place. But I just want to double check real fast. So we got X, Y, and Z. So that's 3 nodes. And then 4, 5, 6. So we've got 6 nodes total if we include the XYZ nodes and all nodes that are direct children of those, and even underneath. So how many do I have in the output pattern? 1, 2, 3, 4, 5, 6. So I've got the same number of nodes. I'm ready to erase all this stuff up top and reattach. 1, 2, 3, 4, 5, 6. Yeah, reattach this into the diagram. So I'm literally just going to erase all this stuff right here. Then I'm going to select all the nodes in the output pattern. And I'm going to move them up to be the new right child of the 44, because that's where originally the Z was. So I'm just going to maybe move these up here real fast and then get that 32 back down where it belongs. Dang you, 32. Actually, it's a little bit too low. Get that maybe a little bit better. How about there? So the last step is we have to recalculate the balance factors to make sure that we have a valid AVL tree. Maybe we have to do another rotation, maybe not, I don't know. Kind of looks like maybe not, but I'm not going to take any chances. So let's do the leaves first. Remember, we have to recompute the balance factors for every node that we just moved. So all the nodes in the output pattern and their immediate children, not anything lower. But so I'm going to say that this 48 node, all the leaves are just going to have a balance factor of 0. That's pretty easy. The 50 is perfectly balanced. Nice. So it's going to have a balance factor of 0. The 78 has one node hanging off the right and nothing on the left, so it's got a 1 there. The 62, again, we're not looking at mass. We're not looking at weight. We're looking at the height of the left subtree versus the height of the right subtree. So this is actually perfectly balanced because the height of the left subtree is 2, and so is the height of the right subtree. Now that we're done with all the nodes that we just moved, we should recursively, or just kind of like walk our way up the tree and recompute all balance factors until we find the root node. Okay, so there's the root node. Only one more thing left to do. The balance factor of the root node is, let's see, left subtree has a height of 2. Right subtree has a height of 3. So the balance factor for the root node is going to be a number 1. Notice how the 44, the root node, got fixed because we rotated a little bit lower. And this is not the fastest tree in the world, but it is considered a log tree because the imbalance is only scaling with a constant factor because we're limiting the balance factors to just the number 1, basically, before we rotate. So what type of rotation did we actually perform? If you looked at my previous video, you should know this already, but maybe I'll duplicate this here and sort of start to maybe annotate it. I'm going to do... Okay, so what is the rotation we did? Well, if we look at the ZYX here, or the XYZ, there's a little bit of a bounce. Actually, let me do orange. There's a little bit of a bounce, right? So that's going to be a double rotation. Or you can imagine that we had to move 2 nodes into position. In order to get the 62 to be the new parent, and the 50 on the left and the 78 on the right, notice how the 78 had to be rotated first. So it's like under the 62, and then the 50 was rotated second underneath. I mean, we snipped off that 54 elsewhere, but long story short, there are 2 nodes that need to be rotated into position for our output pattern. So that's a double rotation. So diagonal bounce or 2 nodes rotated means a double rotation. And then is it a left or a right rotation? Well, if you think about the first node that we rotated, it was the 78. What's going on, my computer? The first node that we rotated was 78, the Z node. So what direction did we rotate that? That was clockwise, so that's a right rotation. So a double right rotation. Another way of looking at it is if we only look at the input pattern, we just look at, these nodes right here, there was kind of a pocket of empty space on the right side, wasn't there? So that's why it's a double right rotation. Another way to think of it is, I'm running out of colors. If we started at the Y node and worked our way up to the Z node, we went up and to the right, so that's a double right rotation also. Either way you cut it, we performed a rotation and now we have a pretty good tree. Okay, let me just double check this is a valid BST. Doop, 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 doop. And it's a valid AVL tree because all the balance factors are okay. Yeah, and in future videos, we're going to do more rotations. I'm probably going to do at least like, 2 or 3 more videos where we just simply rotate, some tree and explain it and work our way through it. If you have an idea for a really gross tree that you want me to rotate in front of you, leave a comment. If I get enough comments, maybe I'll do it. Otherwise, thanks for watching this video. I'll see you in the next one. I hope you learned a little bit of stuff and had a little bit of fun. I'm outie. I'm just simply outie. Hey everybody. Thanks for watching this video again. From the bottom of my heart, I really appreciate it. I do hope you did learn something and have some fun. If you could do me a small little favor, could you please subscribe and follow this channel or these videos or whatever it is you do on the current social media website that you're looking at right now. It would really mean the world to me, and it'll help make more videos and grow this community. So we'll be able to do more videos, longer videos, better videos, or just I'll be able to keep making videos in general. So please do me a kindness and subscribe. You know, sometimes I'm sleeping in the middle of the night and I just wake up because I know somebody subscribed or followed. It just wakes me up and I get filled with joy. That's exactly what happens every single time. So you could do it as a nice favor to me, or you could troll me if you want to just wake me up in the middle of the night. Just subscribe and then I'll just wake up. I promise that's what will happen. Also, if you look at the middle of the screen right now, you should see a QR code which you can scan in order to go to the website, which I think is also named somewhere at the bottom of this video. And it'll take you to my main website where you can just kind of like see all the videos I published and the services and tutorials and things that I offer and all that good stuff. And if you have a suggestion for clarifications or errata or just future videos that you want to see, please leave a comment. Or if you just want to say, hey, what's up? What's going on? You know, just send me a comment, whatever. I also wake up for those in the middle of the night. I wake up in a cold sweat and I'm like, it would really mean the world to me. I would really appreciate it. So again, thank you so much for watching this video, and enjoy the cool music as I fade into the darkness, which is coming for us all. Hey there, let's fart on ourselves. Hello there. Let's rotate an AVL tree because it's frickin' invalid. No. Hey there. Let's maintain an AVL tree. Hey there. Let's maintain an AVL.